Tonight we're going to talk about the emptiness that surrounds you right now, in this very room, at this very moment. Because everything you have ever touched, ever loved, ever known, exists inside a razor-thin bubble of air and warmth and light, floating in something far larger, something silent, something cold beyond imagining. And the moment we step outside that bubble, the universe reveals what it truly is, almost entirely nothing at all. Here's the thing most people don't realize. Space is not simply dark, it is not simply quiet. It is emptier than anything the human mind was built to understand. A vacuum so complete that a single breath of Earth's air, released between the stars, would vanish into a nothingness stretching for trillions of miles in every direction. No sound, no pressure, no warmth to hold on to, just distance, endless and patient, waiting on the other side of our thin blue sky. By the end of tonight, you're going to understand exactly why that emptiness is not the enemy of life, but the quiet condition that made it possible. You will follow the last molecules of our atmosphere as they fade into nothing. You will drift past planets separated by distances the mind can barely hold. You will sit inside the silence that swallowed two lonely spacecraft sailing outward since before you were born, and you will discover that even the emptiest places may not be empty at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. So let's start closer than you think. Right now, wherever you are lying, there is air moving in and out of your lungs without you even asking it to. You don't notice it. You never really have to. It's just there, the way the floor is there, the way gravity is there, holding you gently against your bed without a single thought from you. And that's exactly why it's so easy to forget how strange it really is. Because that air, that soft invisible cushion wrapped around our entire world, is not the rule. It is the exception. Here's the thing most people don't realize. If you could shrink the Earth down to the size of an apple, the layer of air that lets every living thing breathe would be thinner than the apple's skin. That's it. That's all there is. A fragile film wrapped around a spinning rock, hurtling through a darkness that has no skin at all. Beyond that thin layer, there is no more air to speak of, no more warmth held close, no more sound to carry a voice from one place to another. Just silence, waiting patiently, right above our heads. And it starts closer than you'd expect. Airplanes cruise at around 35,000 feet, and already up there, the air is so thin that without a pressurized cabin, you would lose consciousness within moments. Climb higher, past 60,000 feet, past the edge of where even the fastest jets can fly, and the air keeps thinning, until it barely qualifies as air at all anymore. It becomes something closer to a rumour of air, a memory of it. Most people picture the sky as a kind of dome, a blue ceiling that eventually turns black, like flipping a switch somewhere far above the clouds. But that's not how it happens. There is no line, no door, no moment where you could point and say, here, this is where Earth ends and space begins. Instead, the atmosphere fades, slowly, gradually, the way a whispered voice fades into nothing at the far end of a quiet hallway. You're technically still breathing air even 100 miles up, if you could call it that. There are still a few molecules drifting past each other, impossibly far apart, holding on to the last thread of what we call sky. Scientists needed a line anyway, something to mark the boundary, even an artificial one. So they chose a point about 62 miles above sea level, and they named it the Kármán line. Cross it, and by international agreement, you have left the Earth's atmosphere behind. You are now, officially, in space. It sounds so simple when you say it that way. A number, a name, a line on a chart, but think about what that number actually means. 62 miles. If you could drive straight up at highway speed, you would cross that entire boundary of livable, breathable Earth in under an hour. And once you're past it, everything changes. There is no more air pressure pushing back against your body. There is no more oxygen to carry into your blood. There is no more blue sky reflecting sunlight in every direction, scattering it softly the way it does on a calm afternoon. There is only black, a black so deep and so total that the stars stop twinkling, because twinkling is caused by air. Up there, without air, the stars simply burn, steady, unblinking, watching. But here's what makes this moment so unsettling, if you sit with it long enough. That thin blue shell of air, the only thing standing between every person who has ever lived, and the total vacuum of space, is not really protecting us from something far away. It's holding back something that is, in a strange way, right here. Space does not begin at some distant, exotic location that requires years of travel to reach. Space begins about as far above your head as a short commercial flight. It begins closer to you than the nearest major city, closer than most road trips you have ever taken. Think about that for a moment. Somewhere above you tonight, less than 100 miles up, there is already almost nothing. No sound waves to carry a scream, because sound needs air to travel through, and up there isn't enough of it left. No warmth to hold on to, because heat needs matter to move through, and matter is exactly what starts disappearing the higher you climb. It's not some far horizon we're moving toward. It's already here. It's already close. We are living right now on a razor's edge between a fragile pocket of breathable air and a vast, cold nothing that begins practically at our doorstep. And yet, we rarely think about it this way, do we? We look up at a clear night sky and we call it beautiful, peaceful even. We don't usually feel the vertigo of knowing that beauty is actually the absence of almost everything. The black we see between the stars isn't decoration. It isn't a backdrop. It is the true, default condition of the universe. Matter, warmth, air, light, all of it is rare. All of it is the exception carved out against an overwhelming backdrop of emptiness. So before we go any further out, before we follow that emptiness past the moon, past the planets, past the very edge of what our sun can reach, I want you to picture something simple. I want you to picture the air in the room around you right now as a kind of small miracle, a brief, fragile bubble of something, floating inside an ocean of nothing so vast it stretches farther than any number can comfortably describe. That bubble is thin. It is closer to ending than most of us ever stop to consider. And everything you have ever known, every person, every memory, every quiet night like this one, has happened entirely within it. Because once we leave that bubble behind, even by just a little, the universe stops being gentle. It stops holding anything close. And the deeper we go, the more we'll come to understand just how much of what surrounds us, out there in the dark, is not something. It's the absence of everything. And that absence, as strange as it sounds, is where our story really begins. Let's stay close to home a little longer, because there is more to that thin bubble of air than most people ever imagine. It is not one single layer, uniform and simple. It is more like a stack of very different worlds, each one thinner and stranger than the last, piled on top of each other above your head right now. And the deeper we look into that stack, the more we start to understand just how quickly the ground beneath our feet gives way to something else entirely. The part of the atmosphere you actually live in, the part where weather happens, where clouds form, where birds fly and rain falls, is called the troposphere. It reaches up to only about 7 or 8 miles above sea level at most. That's it. Nearly every storm you have ever watched, every sunset you have ever admired, every breath of wind against your face, happened inside that narrow slice. 7 miles. You could walk that distance in a few hours if you tried, and yet within it lives almost all of the weather, and almost all of the air pressure that the entire planet depends on. Above the troposphere lies the stratosphere, cold and still, where commercial jets prefer to cruise because the air up there is calm, smooth, undisturbed by storms below. This is also where the ozone layer lives, a delicate veil of molecules spread so thin that if you compressed all of it down to sea level pressure, it would form a layer only about as thick as the sole of a shoe, that thin, that fragile. And yet it quietly absorbs the most dangerous radiation the sun sends our way, protecting every living thing beneath it, one invisible molecule at a time. Here's the thing most people don't realize about pressure itself. At sea level, the air pushes down on your body with a weight of about 15 pounds on every square inch of you. You don't feel it, because you've never known anything else. It's simply your normal. But climb just 3 miles up, roughly the cruising height of a small aircraft without pressurization, and that pressure has already dropped by more than half. Climb higher still, toward 12 miles, and it drops to a small fraction of what you're used to. The air isn't gone yet, but it is vanishing, quietly, mile by mile, like a tide pulling back from a shore. Weather balloons show us this disappearing act better than almost anything else humans have built. Released from the ground, they climb steadily, expanding as the pressure around them drops, because there is less and less air pushing back to contain them. By the time they reach around 19 or 20 miles up, the pressure has fallen so low that the balloon, now enormous, simply cannot expand any further. It bursts silently, alone, high above every cloud, in air too thin to carry the sound of its own ending back down to the ground. And still, we haven't even reached the strangest part yet. Above the stratosphere lies the mesosphere, the layer where most meteors burn up, streaking briefly across the night sky as shooting stars before disintegrating completely. It sounds almost romantic, doesn't it? But consider what it actually reveals. If a piece of rock falling from space burns up and disappears in that layer, it means there is still enough air up there to create friction, to create heat, to create fire. Even this deep into the fading atmosphere, in one of the coldest layers on Earth, with temperatures plunging to nearly minus 130 degrees Fahrenheit, there is still just enough substance left to consume a falling stone. Above that comes the thermosphere, and here the story gets strange in a different way. Despite being colder in terms of how few molecules are present, the thermosphere can reach blistering temperatures, sometimes over 3,000 degrees Fahrenheit, because the molecules that remain are moving incredibly fast, even though there are so few of them that you would barely feel any heat at all. It's a paradox that quietly reveals something important. At a certain point, our ordinary ideas of hot and cold, of thick and thin, of near and far, simply stop behaving the way they do down here on the ground. The International Space Station orbits inside this very layer, roughly 250 miles above the Earth. And even there, technically inside what we call the thermosphere, there is still just enough leftover atmosphere to create a small amount of drag against the station's structure. Enough that, without periodic boosts from engines, its orbit would slowly decay, pull gently but persistently back toward the Earth. Even 250,000 miles removed from the ground, in a place popularly imagined as the beginning of true space, the last fading whispers of our atmosphere are still there, still touching, still, in some small way, holding on. Beyond the thermosphere lies the final layer, the exosphere, and this is where things become almost impossible to picture using ordinary logic. Molecules here are so far apart from one another that they rarely collide at all. They simply drift occasionally, tracing long invisible arcs before happening to bump into another lonely particle hundreds of miles later. Some scientists consider the exosphere to stretch out as far as 600 miles from Earth's surface. Others argue it fades so gradually that a true edge doesn't really exist, blending almost imperceptibly into the emptiness of interplanetary space itself. So by the time you reach the outer edge of the exosphere, something remarkable has happened without any clear line to mark it. The air that once pressed against your body with 15 pounds of comforting weight per square inch has thinned into something that can no longer even be called air in any meaningful sense. It has become scattered, isolated, a handful of lonely atoms drifting through hundreds of miles of near total vacuum, waiting patiently for something else to happen to them. And that's the strange truth hiding inside everything we've just traced. There was never one single moment where Earth's atmosphere simply stopped. There was only a long, slow fading, layer after layer, each one thinner and stranger than the one before it, until finally there was nothing left to call an atmosphere at all. What waits beyond that fading edge is not another layer, it is not another kind of air, it is the beginning of something else entirely, something that stretches so far beyond anything we've discussed tonight that even 600 miles will soon feel, in hindsight, impossibly small. Picture a rocket climbing, not in the dramatic, fiery moment of launch that you've seen in 100 films, but afterward, minutes later, when the roar has quieted into something closer to a hum, and the curve of the Earth has already begun to bend gently into view outside a small window. This is the part of the journey that rarely gets talked about. The long, quiet climb through air that is disappearing so gradually, so patiently, that the people inside barely notice the exact moment it stops mattering at all. At first, the engines still fight against something. There is still enough atmosphere to create resistance, enough molecules pressed together to generate friction and heat against the hull. Engineers have to account for this precisely, because even a thin remnant of air moving past a spacecraft at thousands of miles an hour can generate enormous heat and force. It seems almost contradictory. The air is nearly gone, and yet what little remains can still scorch metal, still shake a structure hard enough to matter. Emptiness, it turns out, doesn't always feel gentle on the way out, but that resistance fades quickly. By around 50 miles up, the rocket has already left behind the layer where meteors burn into shooting stars. By 80 miles, it has passed the Kármán line, the internationally recognized edge of space itself. And somewhere around this point, something remarkable happens inside the crew's own bodies, something that has nothing to do with instruments or windows. The vibration stops, the turbulence smooths into stillness, not because the engines have changed, but because there is nothing left outside to push against them. No air to shake the frame, no wind to whistle past the hull, just a growing, expanding silence. Here's the thing most people don't realize about that silence. It isn't sudden. It isn't a switch flipped from noise to quiet. It is a slow fade, mile after mile, as fewer and fewer air molecules remain to carry any kind of sound or force at all. Somewhere between 100 and 200 miles above the Earth, the atmosphere has thinned so completely that molecules of oxygen and nitrogen are more likely to drift for miles without ever colliding with one another. Scientists have a phrase for this distance an individual particle can travel before striking another. They call it the mean free path. And down here, on the surface, that path is microscopic, smaller than you could ever perceive. Up there, it can stretch for hundreds of miles. Think about what that really means. On the ground, the air around you is so dense that a single molecule collides with another molecule roughly 10 billion times every second. 10 billion collisions every second in the space it takes you to blink. That density is what allows sound to travel, what allows wind to push against your skin, what allows you to feel the air at all. But 300 miles above your head, a lone molecule might travel for an hour, sometimes longer, before it happens to strike another. It isn't a gas anymore in any way you would recognize. It is closer to a scattering of solitary wanderers, each one alone in the dark, occasionally brushing past another equally lonely traveller. By the time our imagined rocket reaches an altitude of around 300 miles, roughly where the International Space Station orbits, the pressure of what remains has fallen to something almost impossible to describe using numbers that mean anything to us. It has dropped to a fraction so small that scientists prefer scientific notation just to write it down. In practical terms, it means this. If you opened a hatch at that altitude, there would be no rush of escaping air, no dramatic gust, because there is almost nothing left to rush. Just a handful of scattered particles slipping quietly outward into a darkness with room enough to swallow them entirely. And still the climb continues, past 400 miles, past 500. The last remnants of what we once called sky continue to thin, becoming rarer and rarer, until distinguishing between space and remaining Earth atmosphere is no longer a meaningful distinction at all. Some scientists mark 600 miles as the outer edge of Earth's gravitational influence over stray particles. Others argue the transition is so gradual, so seamless, that pinpointing an ending is almost a matter of definition rather than discovery. Either way, what waits beyond that point is no longer a fading version of what we had. It is something else, something new. This is interplanetary space, and here, the numbers stop resembling anything we experience on Earth. In this region, you might find only a handful of particles in every cubic inch of space, compared to the tens of quintillions of molecules packed into that same volume of air at sea level. It's difficult to even compare the two because one is a bustling crowd and the other is closer to a handful of scattered strangers, spread across an area the size of a country. And yet, remarkably, this is not the emptiest place our journey will take us. Not even close, because what makes interplanetary space so strange isn't just its thinness. It's what fills the gaps between those scattered particles. Not air, not fog, not mist of any kind. Just vacuum, pure and nearly perfect, interrupted every so often by a lonely proton or electron drifting outward from the sun, or by a fragment of dust so small it would take a microscope to notice it at all. This is the space your rocket now moves through, not falling through nothing exactly, but drifting through something so sparse that the word emptiness barely does it justice anymore. And here is where the quiet unease begins to settle in, gently, the way it should on a night meant for rest rather than fear. Because if 600 miles above your head, the world has already thinned into near total vacuum, then everything you've ever known, every sound you've heard, every breath you've taken, every gust of wind against your face has happened inside a bubble so small, so fragile, that 600 miles could swallow its entire boundary and barely notice. And beyond that bubble, the true scale of emptiness is only just beginning to reveal itself. Because ahead lies the moon, the planets, and distances so vast that even the numbers we've used so far will soon start to feel almost comfortingly small. Let's pause here for a moment, right at the edge of interplanetary space, and look back the way we came. From this distance, Earth is still visible, still recognizable, a pale blue marble hanging quietly against the black. But something about the view has already changed. The world that once felt so large, so full of oceans and mountains and cities and noise, now looks impossibly small, fragile even, a single, lonely point of blue and white, surrounded on every side by a darkness that stretches farther than the eye can follow. And yet we haven't even reached the moon yet. That's the part that tends to surprise people most. The moon feels close to us, doesn't it? It rises every night. It pulls at our oceans. It has been painted, photographed, and written about more than almost any other object in the sky. It feels like a neighbour, something practically within reach. But the truth of that distance is far stranger than it feels from the ground looking up. Here's the thing most people don't realise. The average distance between the Earth and the Moon is about 238,000 miles. To put that into perspective, you could fit every planet in our solar system, lined up side by side, into the gap between the Earth and the Moon, and there would still be room left over. Mercury, Venus, Mars, all of them together, tucked neatly into that single stretch of open space, with distance to spare. That's not a short walk to a neighbour's house. That's an ocean of emptiness, so vast that even our closest cosmic companion sits impossibly far away. And what fills that gap between us and the moon? Almost nothing. A scattering of dust, so fine it would take specialised instruments to detect it at all. The occasional stray particle from the solar wind, drifting past on its way outward from the sun. But no air, no sound, no resistance to slow anything down. It took the Apollo astronauts roughly 3 days to cross that gap, moving at thousands of miles an hour, through a stretch of space so empty that for those 3 days, they were more isolated from other human beings than any person in history had ever been before. Think about that stillness for a moment. 3 days drifting through a void with almost nothing in it. No sound reaching them from outside the capsule because there was no air to carry any sound at all. No weather, no wind, no days blending into nights the way they do on Earth. Because out there, without an atmosphere to scatter sunlight, the sun simply is or isn't visible, sharp and sudden, with no soft transition between the two. It's a kind of emptiness that swallows not just distance, but the small comforting rhythms we don't even realize we depend on until they're gone. And here's the part that quietly unsettles, even inside such a calm and familiar picture. The 238,000-mile gap between Earth and the Moon isn't unusually empty by cosmic standards. It isn't some rare and special void. It is, in fact, one of the more crowded regions of space you will encounter on this entire journey, simply because it's so close to a planet and a moon, both of which still exert some pull on the wandering dust and particles nearby. Farther out, the emptiness only deepens. The gaps only widen. What feels like an almost incomprehensible void right now will soon start to feel, by comparison, almost intimate. Because beyond the moon, past that already staggering gap, lies something even harder to hold in the mind: the space between the Earth and the Sun itself. That distance, roughly 93 million miles, is called an astronomical unit, and it's used by scientists specifically because regular units, like miles or kilometers, start to lose their meaning at this scale. Numbers that large stop feeling like numbers. They start to feel more like ideas, abstract, slippery, impossible to truly picture, no matter how many times you hear them. Light itself, the fastest thing in the entire universe, takes about 8 minutes to cross that distance from the Sun to the Earth. 8 minutes, which means that every single time you've ever watched a sunrise, you are not looking at the sun as it exists in that exact moment. You are looking at light that left its surface 8 minutes earlier, travelling in total silence through total emptiness, before finally reaching your eyes. In a strange and quiet way, you have never actually seen the present moment of our own star, only its recent past delivered to you across an ocean of nothing. And if the gap between the Earth and the Moon already felt vast, consider this: the distance between the Earth and the Sun is roughly 390 times greater. If you shrank that entire 93 million mile stretch down to fit on a single page, the Earth to Moon distance we just described would be smaller than the width of a single letter on that page. That's the scale we're stepping into now. Not a larger version of what came before, but something categorically different. Something the mind has to stretch itself to even begin holding. So as we drift onward, past the moon, past the quiet, dust-scattered gap that separates us from our only natural satellite, it's worth sitting for a moment with what we've just uncovered. Even the parts of space that feel closest to us, most familiar, most within reach, are already almost entirely empty. The moon isn't floating gently nearby, in some cozy corner of the sky. It sits at the far end of a void large enough to swallow every planet in our solar system, side by side, and still have room left to spare. And ahead of us now lies a gap so much larger still that it will make even this distance feel, in hindsight, almost small enough to touch. So let's talk about the sun for a moment, not as a source of light or warmth, but as something else entirely, something you rarely hear described this way. The sun is not simply sitting quietly at the centre of our solar system, glowing in place. It is constantly shedding pieces of itself outward in every direction at extraordinary speed, a stream of particles, endless and unbroken, pouring off its surface and racing outward into the dark. We call it the solar wind, and the name alone tends to create the wrong picture entirely. Because when you hear the word wind, you probably imagine something like the breeze that moves through trees or the gusts that push against an umbrella on a stormy day. Something with force, something with body. But the solar wind is nothing like that at all. It is made of charged particles, mostly protons and electrons, boiled off the sun's outer atmosphere and flung outward at speeds that can reach nearly 1,000,000 miles an hour. And despite that almost unimaginable speed, it remains, by any standard we understand on Earth, almost nothing. Here's the thing most people don't realize about the solar wind. Near the Earth, roughly 93 million miles from where it began, this stream of particles has spread out so thin that a single cubic inch of interplanetary space near our planet might contain only a handful of these particles at any given moment. Compare that to the air you're breathing right now, where a single cubic inch contains a number so large it would take dozens of digits just to write it down. The solar wind moves faster than almost anything humans have ever built, and yet it carries so little substance that it could never fill a room, never rustle a leaf, never do anything that wind, as we know it, is supposed to do. And still, faint as it is, the solar wind reaches remarkably far. It doesn't stop at Earth. It continues past Mars, past Jupiter, past Saturn, thinning further and further with every additional mile, but never quite disappearing entirely. It carries with it a kind of invisible signature of the sun itself, a whisper of solar material stretched out across billions of miles of otherwise empty space. In a strange way, the sun's influence extends far beyond the warmth and light we associate with daytime. It reaches out quietly into some of the emptiest regions our solar system has to offer. We've actually built spacecraft specifically to study this thin, fast-moving stream up close. The Parker Solar Probe, launched in 2018, was designed to fly closer to the sun than any human-made object ever had before, plunging directly into the outer edges of the solar atmosphere itself, moving fast enough to survive temperatures that would destroy almost anything else humans have built. What it found only deepened the mystery surrounding this strange, thin ocean of particles. The solar wind doesn't flow smoothly and evenly, the way water moves through a river. It gusts, it surges, it carries sudden bursts of energy and speed that scientists still don't fully understand, even decades after first detecting it. But here's where the story turns quietly unsettling again, in that gentle way that keeps returning to us tonight. Despite reaching for billions of miles, despite moving at speeds that would carry it across the entire United States in a matter of seconds, the solar wind is still overwhelmingly, achingly empty. It is a wind you could never feel, in a space so vast that even at these staggering speeds, the particles rarely, if ever, encounter one another. They are far too spread out, far too isolated, each one travelling essentially alone, across distances that dwarf anything we experience in daily life. And this raises a strange, almost philosophical question, doesn't it? If something can move that fast and reach that far, and still be considered almost nothing, what does that tell us about the scale we're actually dealing with? It tells us that the emptiness we've been describing isn't simply about stillness or silence. It's about scale so enormous that even fast, energetic, far-reaching phenomena still measure as close to nothing at all. The solar wind isn't weak because it lacks energy. It's weak because the space it moves through is almost incomprehensibly vast, swallowing its substance the way an ocean might swallow a single drop of rain. This region, filled with the sun's faint outward breath, is what scientists call interplanetary space, and it makes up the overwhelming majority of the volume within our solar system. Think about that for a moment. The planets themselves, Mercury, Venus, Earth, Mars, all the way out to distant Neptune, occupy only a tiny, almost negligible fraction of the total space contained within our solar system's boundaries. Nearly everything else, the vast, overwhelming majority of it, is this same thin, drifting soup of solar wind particles, an empty vacuum, stretching between the worlds like an ocean, surrounding a scattering of small, isolated islands. And it's a strange thought to sit with, especially at night, especially when everything around you feels solid and close and real. Our entire solar system, home to 8 planets, dozens of moons, countless asteroids, and comets, is mostly just this. Emptiness laced faintly with the outward breath of a single star, spreading outward in every direction for billions upon billions of miles. The planets are not the main feature of this space. They are rare exceptions floating within it, small pockets of substance scattered across an overwhelming sea of near nothing. So as we continue outward now, past this faint solar wind, past the reach of the sun's quiet breath, it's worth carrying this feeling with us. Even here, even this close to our own star, emptiness is already the dominant truth of everything around us. And the deeper we travel, the more that truth will only sharpen, until the gaps between the planets themselves reveal a scale of emptiness that makes even the solar wind's vast reach feel, by comparison, almost intimate. Let's keep moving outward, past the reach of the solar wind, toward the planets themselves. And let's start with Mars, because Mars is the planet most often talked about as humanity's next destination. It feels, in conversation, almost close, almost reachable, something we could simply decide to visit, the way you might decide to visit another country. But the actual distance between Earth and Mars tells a very different story, one that depends entirely on where each planet happens to be in its orbit at any given moment. At its closest possible approach, Mars can come within about 33 million miles of Earth. That already sounds enormous, and it is, but here's the part that rarely gets mentioned. That closest approach is rare and brief and depends on a precise alignment of 2 planets moving at different speeds around the Sun. Most of the time, the distance between Earth and Mars is far greater than that. At its farthest, when the 2 planets sit on opposite sides of the Sun from each other, the gap can stretch to more than 250 million miles. The same 2 planets, the same 2 neighbours, separated by a distance that can vary by hundreds of millions of miles, depending on nothing more than timing. Think about what that means for anyone hoping to travel there. A spacecraft can't simply point itself at Mars and go in a straight line, the way you might drive toward a distant mountain. It has to account for the fact that both planets are moving, constantly, along their own separate paths around the Sun. Engineers have to calculate a curved trajectory, launching not toward where Mars is right now, but toward where Mars will be months later, once the spacecraft finally arrives. Even with the most efficient possible routes, a journey to Mars still takes somewhere between 6 and 9 months. Half a year or more, drifting through open space, just to reach our nearest planetary neighbour. And Mars is close. That's the part that starts to feel unsettling once you sit with it. Compared to what lies beyond, Mars is practically next door. Because past Mars lies the asteroid belt, a wide scattered region we'll explore more closely soon. And beyond that, the gas giants begin. Jupiter, the largest planet in our solar system, sits at an average distance of about 484 million miles from the Sun. From Earth, depending on our relative positions, that distance to Jupiter can stretch even further, sometimes exceeding 600 million miles. Here's the thing most people don't realize about a distance that large. Light itself, moving at over 670 million miles an hour, the fastest speed anything in the universe is capable of reaching, takes over 40 minutes just to cross the average gap between the Sun and Jupiter. 40 minutes for something with no mass, no resistance, nothing slowing it down at all. If you sent a radio signal from Earth to a spacecraft near Jupiter and waited for a reply, you could easily wait the better part of an hour before hearing anything back. An entire conversation stretched out across nearly 90 minutes, just to exchange a single question and a single answer. And Saturn lies even farther still, at an average distance of roughly 886 million miles from the Sun. Light takes well over an hour to cross that gap. The Cassini spacecraft, which studied Saturn and its rings for over a decade, sent its data back to Earth across that same staggering distance, every single signal travelling through more than an hour of pure empty silence, before finally reaching a waiting antenna somewhere on our small blue planet. Imagine capturing an extraordinary photograph, one that could rewrite what we understand about a distant world, and then waiting over an hour, alone, in the dark, simply for that image to complete its journey home. And still, we haven't reached the edge yet. Uranus sits nearly twice as far from the Sun as Saturn, and Neptune, the outermost recognised planet in our solar system, orbits at an average distance of about 2,800,000,000 miles from the Sun. Light takes over 4 hours to cross that gap, 4 hours at the fastest possible speed in the entire universe, just to travel from our star to its farthest planetary neighbour. When Voyager 2 sent back its first close images of Neptune in 1989, those images had already been travelling through empty space for over 4 hours before they finally reached Earth, carrying with them the very first close look humanity had ever gotten of that distant, icy world. And here's what makes all of this quietly overwhelming. Once you try to hold the whole picture in your mind at once, if you shrank the entire solar system down to fit on a single football field, with the Sun sitting at one end, Earth would be only a few steps away, barely past the goal line. Mars would be a few steps further still, but Jupiter would already be near midfield, Saturn would be approaching the far end, and Neptune, our solar system's outermost known planet, would be standing at the very edge of the opposite goal line, separated from tiny distant Earth by the entire length of the field. And what fills all of that space across that entire imagined football field between each of those small scattered points representing planets? Almost nothing. No air, no sound, no resistance, just the faint, thinning breath of the solar wind we described earlier, and vast, uninterrupted stretches of true vacuum, patiently holding each planet at a careful, lonely distance from all the others. The planets themselves, for all their size and grandeur, occupy only the tiniest fraction of the space contained within our own solar system's boundaries. So before we continue outward, toward the very edge of where our Sun's influence finally fades away entirely, it's worth sitting with this feeling for a moment. Even within our own cosmic neighbourhood, among planets we've studied for centuries, among worlds close enough that spacecraft have visited nearly all of them, the emptiness between those worlds is almost total. Jupiter and Saturn, Uranus and Neptune, each one drifting alone through hundreds of millions of miles of open dark, closer to isolated islands, scattered across an endless ocean than neighbours sharing any kind of common shore. And ahead of us now lies a region often imagined as crowded and chaotic, but which, as we're about to discover, turns out to be almost the opposite of everything you've probably pictured. Somewhere between Mars and Jupiter, drifting along that same imagined football field we described a moment ago, lies a region you have almost certainly seen before, even if you've never realised it. It shows up in movies constantly. A spacecraft weaving desperately between tumbling boulders, dodging one narrow miss after another, rocks colliding and crashing in the background as pilots grip their controls in tension. It makes for thrilling cinema, and it is almost entirely fiction. This is the asteroid belt, and here's the thing most people don't realise about it. It is not a dense, chaotic field of rock, crowded so tightly that navigating through it requires careful, skillful piloting. It is instead one of the emptiest regions we've encountered so far on this journey. The asteroid belt contains millions of individual objects, yes, ranging from tiny pebbles to the dwarf planet Ceres, which alone accounts for roughly a third of the belt's entire estimated mass. But millions of objects scattered across a region of space that spans hundreds of millions of miles results in something very different from what Hollywood has trained us to imagine. To understand just how sparse this region really is, consider this. The asteroid belt stretches across a band of space between Mars and Jupiter that is roughly 100 million miles wide. Within that entire vast expanse, the average distance between any two sizable asteroids is estimated to be well over 600,000 miles. 600,000 miles? That is more than twice the distance between the Earth and the Moon, just to travel from one asteroid to its nearest sizable neighbour. If you were actually flying a spacecraft through the belt, you likely wouldn't see a single asteroid up close during your entire crossing, let alone need to dodge one. In fact, every single spacecraft humanity has ever sent through the asteroid belt, and there have been several, including missions bound for Jupiter and beyond, has passed through it without any special manoeuvring at all. No dodging, no weaving, no dramatic near misses. Engineers simply plot a straight course and fly through, because the odds of an accidental collision are almost impossibly small, smaller than most people would ever guess, given how the region is so often portrayed. NASA has described crossing the belt as one of the least eventful parts of many outer solar system missions, precisely because there is so little there to actually encounter. And here's where the deeper unease starts to creep in, quietly, the way it tends to on this journey. If the asteroid belt, a region specifically named and defined because of the objects it contains, is still overwhelmingly empty space, what does that tell us about literally everywhere else we've travelled tonight? It tells us that even the parts of the universe we associate most strongly with density and clutter and crowded chaos are, in truth, almost entirely vacuum, interrupted only occasionally by small scattered fragments of rock and metal drifting alone through hundreds of thousands of miles of open dark. Some of these asteroids are enormous. Vesta, the second largest object in the belt, stretches over 300 miles across, nearly the width of an entire American state. Others are barely larger than a grain of sand, drifting silently, unnoticed, for millions of years without ever being observed by any telescope or spacecraft. And between all of them, in every direction, for hundreds of thousands of miles at a stretch, there is nothing. No sound, no resistance, no sense of crowding whatsoever. Just an occasional, isolated fragment, tumbling slowly through a silence so complete it's almost impossible to picture. The Dawn spacecraft, which visited both Vesta and Ceres in the 2010s, spent months orbiting each object, capturing detailed images of cratered, ancient surfaces that had remained largely undisturbed for billions of years. And in the vast stretches of space between those two targets, Dawn encountered essentially nothing else worth mentioning. No debris fields, no clustered rock formations, just the same thin scattering of distant, isolated objects we've come to expect by now, each one existing in near total isolation from every other body around it. It's worth pausing here, because this particular myth, the crowded, chaotic asteroid field, reveals something important about how easily our imaginations fill in gaps that reality simply doesn't support. We picture space as busy because busy is what we know. Busy is our normal here on Earth, surrounded by other people, other cars, other sounds, other movement, constantly. But space doesn't share that assumption. Space defaults to emptiness, overwhelmingly and almost without exception, and even regions defined by the objects scattered within them turn out to be governed, first and foremost, by the vast distances separating those objects from one another. So as we leave the asteroid belt behind us now, drifting onward past Ceres and Vesta and the countless smaller fragments too small to ever be named, carry this thought forward with you. Even here, in a region literally named for the rocks it contains, rock is the exception. Emptiness is the rule. And the deeper this journey takes us past Jupiter, past Saturn, toward the very outer edges of our sun's reach, that same quiet truth will only continue to reveal itself, again and again, in forms even harder to fully imagine. Past Jupiter now, past Saturn, past Uranus, past Neptune, drifting beyond every planet our solar system has to offer. And still remarkably, we are not yet in what most scientists would call true interstellar space. Because the Sun's influence doesn't simply end at the last planet's orbit. It continues outward, fainter and fainter, in the form of that same solar wind we described earlier, still pushing weakly against the surrounding darkness, still carrying the faintest whisper of our star's presence into a region far beyond anything we've discussed so far. This entire bubble, carved out by the Sun's outward breath, is called the heliosphere. Picture it like a kind of vast, invisible balloon, with our star at its centre, and its edges extending far beyond the last planet, out into the space between the stars. Within this bubble, the solar wind, thin as it already is, still holds a kind of quiet dominance over the surrounding vacuum. But nothing extends forever. Eventually, even the Sun's faint breath runs out of strength, pushing against something it can no longer overcome. And that boundary, the outer edge of the heliosphere, is called the heliopause. Here's the thing most people don't realize about that boundary. It isn't a wall. It isn't a line you could see or touch or photograph in any conventional sense. It's a gradual transition, a place where the outward pressure of the solar wind finally weakens to the point that the pressure of the interstellar medium, the thin gas and dust drifting between the stars, begins to win out instead. Scientists estimate this transition occurs somewhere around 11 to 18 billion miles from the Sun, depending on the exact direction you're travelling and the current strength of solar activity at any given time. 11 to 18 billion miles. Let that number sit for a moment, because it is almost impossible to hold in the mind using any comparison from ordinary life. Remember Neptune, sitting nearly 3 billion miles from the Sun, so far away that light itself took over 4 hours just to make the crossing. The heliopause lies 4 to 6 times farther than that, an entire additional Neptune's worth of distance, stacked several times over, just to reach the outer edge of where our own Sun's influence finally gives way to something else entirely. And we know precisely how far this boundary lies because 2 small spacecraft, launched in 1977, actually crossed it. Voyager 1 and Voyager 2, originally designed for a relatively brief mission to study Jupiter and Saturn up close, kept going. Decade after decade, they continued outward, long after their original mission objectives had been completed, long after most of the scientists who built them had expected the spacecraft to still be functioning at all. And in 2012, Voyager 1 became the first human-made object in history to cross the heliopause, entering, for the very first time, the space between the stars. Think about the scale of patience contained in that single achievement. Voyager 1 launched in 1977, and it took 35 years, more than 3.5 decades of continuous travel through the solar system and beyond, just to reach that boundary. 35 years, moving at roughly 38,000 miles an hour, one of the fastest speeds any human-made object has ever achieved. And it still took over 3 decades simply to cross the outer edge of our own Sun's zone of influence. That's not a short trip to the edge of the neighbourhood. That's most of a human lifetime, spent travelling in one continuous direction, just to leave home. And here's where the quiet unease deepens again, the way it keeps returning to us throughout this journey. As Voyager 1 approached the heliopause, its instruments recorded something remarkable. The density of charged particles from the Sun, the same solar wind we described earlier, began dropping sharply, while the density of particles from outside the solar system, cosmic rays originating from distant, ancient stellar explosions elsewhere in the galaxy, began rising just as sharply. It was as though the spacecraft had stepped, gradually but unmistakably, out of one ocean and into another, out of the Sun's quiet breath and into something colder, older, and far less familiar. Voyager 2 followed a similar path 6 years later, in 2018, crossing the heliopause along a slightly different trajectory and confirming much of what Voyager 1 had already discovered. Together, these two small aging spacecraft, each barely larger than a small car, each still running on plutonium power sources, slowly fading after more than 4 decades of continuous operation, became the only human-made objects to ever leave the protective bubble of our own star and enter the space beyond. Everything else humanity has ever built, every satellite, every space station, every crewed mission has remained entirely within the heliosphere, still cradled in some small way by the outward breath of our own sun. And what lies beyond that boundary in the region the Voyagers now travel through is not simply more of the same emptiness we've already described. It is something colder, something quieter, something that exists almost entirely outside the influence of any single star at all, drifting instead through the vast, ancient spaces between entire stellar systems. This is interstellar space in the truest sense of the word, and it represents a threshold unlike anything we've crossed so far tonight. Not simply another layer of emptiness stacked on top of the last, but an entirely different regime, governed by forces and distances that make even the vast gaps between our own planets feel, in comparison, almost cozy. So before we follow those two lonely spacecraft any further into that deepening darkness, it's worth pausing here at the very edge of our sun's reach and appreciating what this threshold actually represents. 11 to 18 billion miles from home, humanity's oldest surviving spacecraft finally slipped free of everything familiar, everything shaped and touched by our own star, and entered a silence so complete, so ancient, that it had been waiting there, undisturbed, for longer than human civilization has existed. And it is into that very silence that our story now continues. Before either Voyager crossed that final threshold into interstellar space, engineers back on Earth made a decision that, in hindsight, feels almost impossibly poignant. They attached a golden record to the side of each spacecraft, a physical disc plated in gold to survive the ravages of time, containing sounds and images meant to represent humanity to whoever or whatever might one day find it. Greetings in dozens of languages, the sound of rain, a mother's laughter, music from cultures scattered across the entire planet, all of it sealed onto a small golden disc and sent outward, into a silence so vast it may never be heard by anyone at all. Here's the thing most people don't realize about that golden record. It wasn't really designed with the expectation of being found. The scientists and engineers who created it understood, even then, just how staggeringly empty the space ahead truly was. The odds of the Voyager spacecraft ever passing close enough to another star system for anyone to notice, let alone recover and play that record, are so small they barely register as a possibility at all. And yet they built it anyway, carefully, lovingly, as though the act of sending a message into that silence mattered, regardless of whether anyone would ever hear it. That single decision captures something important about what awaited these two small spacecraft once they finally crossed the heliopause. Because interstellar space isn't just distant, it is isolated in a way that's difficult to fully absorb. Once Voyager 1 slipped past that boundary in 2012, it entered a region where the nearest star system, other than our own, sits over 4 light-years away. That's roughly 25 trillion miles. At Voyager's current speed, it would take more than 70,000 years just to cross that distance, and even then, it isn't actually headed toward Alpha Centauri at all. It's drifting slowly toward a different, more distant star entirely, one it won't approach for tens of thousands of years still. And here's where the isolation becomes almost impossible to fully comprehend. In interstellar space, the density of matter drops even further than anything we described in the outer solar system. Where interplanetary space near Earth might contain a handful of particles in every cubic inch, the interstellar medium beyond the heliopause often contains fewer than 1 particle per cubic inch, sometimes far fewer. It is emptier than the best vacuum chambers humans have ever built here on Earth, emptier than anything our own laboratories, with all our advanced technology, have managed to replicate in a controlled setting. Voyager, out there, is quite literally travelling through a vacuum more perfect than anything we can create at home. The instruments aboard both spacecraft continue recording data, even now, decades after launch, sending faint radio signals back across billions of miles to be picked up by giant dish antennas here on Earth. But those signals take longer and longer to arrive with every passing year, as the spacecraft continue drifting further outward. Today, a single message from Voyager 1 takes over 22 hours just to reach Earth, travelling at the speed of light the entire way. 22 hours for a signal moving as fast as anything in the universe is capable of moving. Imagine sending a single word out into the dark and waiting nearly a full day just to know it arrived. And for years at a stretch, what those instruments record is remarkably close to nothing at all. Long stretches of near total emptiness, interrupted only occasionally by a faint fluctuation in the interstellar magnetic field, or a distant burst of plasma from some ancient stellar event. Its origin, sometimes untraceable, its cause sometimes never fully explained. Scientists studying the data have described entire years passing with almost no notable readings whatsoever. Just quiet, steady confirmation that the spacecraft continues moving through a void so complete that even scientific instruments, designed specifically to detect the faintest possible signals, find themselves recording silence far more often than anything else. Here's the thing that tends to settle over people once they really sit with this. Voyager 1 and Voyager 2 are, right now, tonight, the most isolated objects human beings have ever created. Farther from any other living thing, farther from any other planet, farther from any warmth or sound or light than anything else we have ever built or sent anywhere. They carry with them a golden record, full of laughter and music and greetings meant for someone, anyone, who might one day find them. And they drift silently, through a darkness so complete, so ancient, so overwhelmingly vast that the odds of that golden record ever being discovered remain achingly, almost tragically, small. And yet, there is something quietly beautiful buried inside that isolation too, because both spacecraft are still, even now, technically functioning. Their radio transmitters, though weakening year after year as their power sources slowly fade, still manage to send a faint signal home. Scientists still listen, still receive those signals, faint as they are, and still confirm that somewhere out there, farther from Earth than any human voice has ever travelled, two small machines built by human hands continue moving forward, carrying a message meant for no one in particular, and everyone, all at once. Before long, within the next decade or so, both spacecraft will finally run out of power entirely. Their instruments will go dark, their transmitters will fall silent, and they will continue drifting forever, silent and cold, carrying their golden records through a darkness that may never again register their presence in any meaningful way. No signal, no sound, no confirmation that they ever existed at all, except for the fact that they will keep moving indefinitely, long after every person who built them and everyone listening to this story tonight is gone. And it's worth carrying that image forward as we continue this journey ourselves, deeper into the space those two spacecraft now travel through. Because what Voyager found, more than anything else, was confirmation of just how total, how complete, how staggeringly vast the silence between the stars truly is. Not an occasional emptiness interrupted by frequent discoveries. A near total, near permanent quiet, broken only rarely by faint signals from a sun growing dimmer with every billion miles left behind. Let's leave Voyager drifting there for a moment, carrying its golden record through the dark, and turn our attention to the stars themselves, specifically to the nearest one. Because if you've ever looked up on a clear night and wondered just how far away the closest star to our own sun really is, the answer tends to land differently once you've already travelled, in your mind, all the way to the edge of the heliosphere. It turns out that even after crossing 11 to 18 billion miles just to leave our own solar system behind, we have barely begun the true journey to anywhere else at all. The nearest star system to our own is called Alpha Centauri, and within it lies Proxima Centauri, the single closest star to our Sun. The distance between us and that star is a little over 25 trillion miles. Trillion, not billion, an entirely different order of magnitude from anything we've discussed so far tonight. So large that even the staggering numbers describing our own solar system start to feel almost quaint by comparison. To put it plainly, if the distance from the Sun to Neptune, that 4-hour journey for light, represents a single step, then the distance to Proxima Centauri would represent a walk of well over 6,000 of those same steps. Here's the thing most people don't realise about that distance. Light itself, the fastest thing that exists anywhere in the universe, takes a little over 4 years to cross it. 4 years, not minutes, not hours, years. Which means that the light reaching your eyes tonight, if you were to look toward Alpha Centauri in a clear night sky, left that star system before many of the events you remember from several years ago had even happened yet. You are not looking at that star as it exists right now. You are looking at a memory carried across trillions of miles of near total darkness, delivered to you years after it began its journey. And the space between here and there is not simply more of the same interstellar medium we described near Voyager's current position, thin and quiet and occasionally interrupted. It is, if anything, even emptier still, for almost the entire length of that unimaginable distance. Scientists estimate that the density of matter in the space between our solar system and Alpha Centauri averages out to less than 1 atom per cubic inch across most of that journey. Less than 1 atom in a space you could hold in your closed fist. Multiply that emptiness across 25 trillion miles, and you begin to understand why even our fastest spacecraft, moving faster than any bullet ever fired, would still take tens of thousands of years just to complete that single crossing. Here's the thing most people don't realise, and it's the kind of fact that tends to sit uncomfortably once you really absorb it. Voyager 1, moving at roughly 38,000 miles an hour, one of the fastest speeds any human-made object has ever reached, would still take more than 70,000 years to travel a distance, equivalent to reaching Alpha Centauri, if it were even headed in that direction, which it is not. 70,000 years, longer than the entire span of recorded human history, several times over, just across the gap to our single nearest stellar neighbour. And Alpha Centauri isn't even unusually distant. It's the closest star system there is, and what fills all 25 trillion miles of that gap for almost the entire distance is a cold beyond anything experienced anywhere on Earth. The average temperature of the interstellar medium in the vast empty stretches between star systems hovers just a few degrees above absolute zero, the theoretical point at which all molecular motion stops entirely. We're talking about temperatures near negative 450 degrees Fahrenheit. Brutally cold. Cold enough that most gases would freeze solid instantly. Cold enough that heat, in any meaningful sense, simply does not exist there, except in rare, isolated pockets where a star's radiation happens to reach. And it is silent. Not silent in the way an empty room feels quiet, where sound is merely absent for a moment. Silent in the truest, most complete sense the word can carry, because sound itself requires molecules pressed closely enough together to carry a vibration from one point to another, and out there, across trillions of miles at a stretch, those molecules are simply too far apart to carry anything at all. No sound has ever travelled across that gap. No sound ever will, not in any way our ears could recognise. It is a silence that has existed, unbroken, for longer than stars themselves have burned. Think about what it would actually mean to travel through that space if such a journey was somehow possible for a human being. No stars would rush past your window the way they do in films, streaking by in colourful blurs. They would remain distant, fixed, barely shifting at all across years of continuous travel, because even at extraordinary speeds, the distances involved are so large that movement itself would feel almost imperceptible against such a vast backdrop. You would drift for years through a cold, silent darkness, with your own star growing fainter behind you, and the star you're travelling toward barely growing brighter ahead, the entire journey unfolding at a pace too slow for the human mind to properly register as motion at all. And this is where the emotional weight of tonight's exploration begins to deepen, gently, the way it should on a night meant for rest, rather than fear, because this vast, cold, silent gap between the stars is not some rare or unusual pocket of the universe. It is, in fact, the default condition of almost everything that exists beyond our own small solar system. Stars themselves, for all their brightness, for all the light and warmth and wonder we associate with them, are rare, isolated points of exception, scattered like distant campfires across an otherwise endless and freezing dark. So before we go any further, before we start asking exactly how few atoms actually occupy that space, and what it might mean for a universe built almost entirely from this kind of profound absence, I want you to sit for just a moment with the image we've built together tonight. 25 trillion miles of near total vacuum, cold beyond anything imaginable, silent beyond anything you have ever experienced, separating our small, warm, breathing world from even its very closest neighbour among the stars. And somewhere within that vast darkness, two small golden-plated spacecraft continue drifting, carrying with them the only sounds that darkness has ever known. So how do we actually know any of this? How do scientists measure something as elusive as a single atom, drifting alone across trillions of miles of open darkness, far beyond the reach of any telescope's direct view? It's a fair question, and the answer reveals something almost as fascinating as the emptiness itself. Because measuring nothing, it turns out, requires some of the most careful, patient, and clever science human beings have ever developed. One of the most elegant methods involves something called pulsar dispersion. Pulsars are the collapsed remains of massive stars, spinning rapidly and emitting powerful, regular pulses of radio energy, like cosmic lighthouses sweeping their beams across the galaxy. When that radio energy travels toward Earth, it has to pass through whatever thin material happens to lie in its path, however sparse that material might be. And here's the remarkable part. Different wavelengths of that radio pulse travel at very slightly different speeds when passing through even the faintest trace of interstellar gas, arriving at our telescopes microseconds apart from one another. By measuring that tiny delay, scientists can calculate, with startling precision, exactly how much material the signal passed through along its journey, even when that material amounts to only a handful of atoms spread across trillions of miles. Here's the thing most people don't realize about what these measurements actually reveal. Within our own galaxy, in what astronomers call the interstellar medium, the average density comes out to roughly 1 atom per cubic centimetre. A cubic centimetre is about the size of a sugar cube. 1 atom, floating alone, somewhere within a volume you could hold between 2 fingers. And even that counts as relatively crowded by the standards of deep space. Compare that to the air around you right now, where a single cubic centimetre contains roughly 25 quintillion molecules, a number so large that comparing the two almost breaks down entirely as a meaningful exercise. To make that comparison feel more real, imagine taking every single molecule of air inside a small bedroom and then spreading those molecules out evenly across the volume of the entire Earth. That's roughly the kind of dilution we're talking about when we compare ordinary air to the average density of interstellar space. Not slightly less crowded, not noticeably thinner, diluted by a factor so extreme that the two situations barely belong in the same conversation about what a gas even is. and within that already sparse interstellar medium, density varies enormously depending on where exactly you happen to be. Some regions, called molecular clouds, are relatively denser, sometimes containing hundreds or even thousands of particles per cubic centimetre, dense enough, in these specific cosmic terms, to eventually collapse under their own gravity and form new stars. These are the stellar nurseries, the birthplaces of future suns and future planets, and yet even at their densest, these clouds remain far, far thinner than the best vacuum humans have ever managed to produce in an Earth-based laboratory. But venture into what astronomers call the intercloud medium, the vast stretches of space between those denser molecular clouds, and the numbers drop dramatically, sometimes to less than a tenth of a particle per cubic centimetre. In these regions, an atom might drift for what would translate to years in terms of the distance it travels, before ever encountering another atom to interact with. It exists in almost total isolation, a solitary particle moving through a darkness so complete that its next collision might not occur until long after any human observer watching it began would have grown old and died. Here's where the feeling of quiet vertigo deepens again, gently, the way it tends to throughout this journey. Because everything solid you've ever touched, every breath you've ever taken, every warm and tangible thing in your entire life is built from atoms that happen to find each other, cluster together, and remain close enough to form matter as we understand it. But that closeness, that clustering, is not the default state of atoms in the universe. It is the rare exception. Most atoms, scattered across most of the universe, exist in something closer to what we just described. Alone, isolated, drifting for unimaginable distances before ever brushing against another particle at all. Scientists have also used another method to measure this emptiness, one that involves looking at distant stars and analysing the very faint absorption lines in their light. As starlight travels toward us across interstellar distances, it occasionally passes through faint traces of gas and dust, and that material absorbs very specific wavelengths of light, leaving behind a kind of chemical fingerprint we can detect and study using spectroscopy. Through this method, astronomers have identified not just hydrogen, the most common element in the universe, but trace amounts of other elements as well, scattered thinly across distances that would otherwise seem entirely, perfectly empty. And this is perhaps the most important realization to carry forward from everything we've measured so far tonight. Interstellar space is not a true, perfect vacuum in the strictest scientific sense of that term. It contains something. Atoms, molecules, faint traces of dust left behind by ancient supernova explosions that occurred long before our own sun ever formed. But those traces are so sparse, so overwhelmingly outnumbered by empty space itself, that for almost every practical purpose, calling it nothing feels more accurate than calling it something. It exists in that strange, unsettling middle ground between true emptiness and matter, a place our everyday language and everyday intuition were simply never built to describe. So as we continue this journey outward now, past the edges of individual star systems, past even the space between neighbouring stars, and into the vastly larger scale of the galaxy itself, carry this measurement with you. One atom in the space of a sugar cube. That number will keep echoing throughout everything that follows, because it turns out that even galaxies themselves, packed as they appear with billions of stars, are built from precisely this same overwhelming, quiet, patient emptiness, stretched across a canvas so large that even the words trillion and quintillion begin to lose their meaning entirely. Let's step back now, back, far enough that individual stars stop being the subject of our attention and entire galaxies take their place instead. Because everything we've explored so far tonight, every billion-mile gap, every trillion-mile crossing, every lonely atom drifting through a sugar cube's worth of space has taken place within a single galaxy, our galaxy, the Milky Way. And as vast as that has already felt, it turns out we've only been exploring a single neighbourhood within something almost incomprehensibly larger still. The Milky Way contains somewhere between 100 billion and 400 billion stars, scattered across a disk roughly 100,000 light-years wide. A single light-year, remember, is already about 6 trillion miles, so multiply that out, and you begin to sense the true size of the structure we call home. And yet, here's the thing most people don't realise, even about our own galaxy. Despite containing hundreds of billions of stars, the Milky Way is still, overwhelmingly, mostly empty space. Think about it this way. If you shrank the Sun down to the size of a single grain of sand and placed it on a table, the next nearest star, Proxima Centauri, would need to be represented by another grain of sand placed roughly 4 miles away. 4 miles between 2 grains of sand, just to represent the actual scale of distance between our nearest stellar neighbours. And that spacing, believe it or not, is considered relatively dense compared to the outer regions of our galaxy, where stars drift even further apart from one another, separated by even greater stretches of cold, dark, empty space. Here's a number that tends to land hard once you really sit with it. If you calculated the actual volume occupied by every star in the Milky Way, adding together the physical size of each one of those hundreds of billions of suns, and compared that total to the entire volume of space contained within the galaxy's boundaries, stars would account for something far, far less than even a tiny fraction of a single % of the total space available. The rest, the overwhelming, staggering majority of our own galaxy's volume, is exactly the same kind of thin, cold, near-total vacuum we described drifting between our Sun and Alpha Centauri. Multiplied, essentially, across hundreds of billions of individual gaps. And if a single galaxy is this empty, what happens when we zoom out even further, to the space between galaxies themselves? The nearest large galaxy to our own is Andromeda, and it sits at a distance of roughly 2.5 million light-years away. 2.5 million light-years. That number is so large that it stops feeling like a distance at all and starts feeling more like a length of time, because it effectively is one. The light reaching our telescopes from Andromeda tonight left that galaxy 2.5 million years ago, long before modern humans even existed as a species. And what fills that unimaginable 2.5 million light-year gap between our galaxy and our nearest large galactic neighbour? Almost nothing, in a way that makes even interstellar space look comparatively crowded. This region is called intergalactic space, and its density drops even lower than what we found drifting between individual stars. Some estimates suggest fewer than 1 atom per several cubic meters in the emptiest stretches between galaxies, a dilution so extreme that our earlier comparison, 1 atom per sugar cube, would need to be stretched out across a space the size of a small room, just to represent how sparse this region truly becomes. Here's the thing that tends to settle over people once they hold this image fully in mind. Galaxies themselves, despite containing hundreds of billions of stars each, are still, relative to the space surrounding them, remarkably small and isolated points of light, scattered across an almost incomprehensibly vast dark ocean. If you could shrink the entire observable universe down to fit inside a single room, galaxies would appear as nothing more than scattered dust motes, tiny and sparse, separated by distances that would dwarf the room itself many times over. The universe at every single scale we've examined tonight, from the air around your own body to the space between entire galaxies, follows the exact same pattern. Emptiness, overwhelming and total, interrupted only rarely, only briefly, by small, isolated pockets of something. And yet, strangely, galaxies do not simply drift apart from each other in complete isolation. They cluster together, gravitationally bound across these enormous distances, forming groups and clusters and superclusters, vast cosmic structures stretching across hundreds of millions of light years. Our own Milky Way belongs to a small collection of galaxies called the Local Group, itself part of a much larger structure, known as the Laniakea supercluster, a name that means, fittingly, immeasurable heaven in Hawaiian. Even within these massive structures, though, the same rule applies. The galaxies themselves occupy a vanishingly small fraction of the volume, while emptiness stretches patient and complete across everything between them. This raises a question that scientists have wrestled with for decades now, one that will carry us into the next part of our journey tonight. Because gravity is what holds these galaxies together across such staggering distances, binding them into clusters and superclusters despite the overwhelming emptiness separating them. But when astronomers calculate exactly how much visible matter exists within these structures, stars, gas, dust, planets, all of it combined, the gravitational pull produced by that matter alone isn't nearly strong enough to explain the way galaxies actually move and cluster together. Something else has to be there, something invisible, something hiding quietly inside all of this apparent nothingness. So let's sit with that question for a moment, the one we left hanging at the edge of the last chapter. If galaxies cluster together across hundreds of millions of light years, held in place by gravity, but the visible matter within them isn't nearly enough to produce that much gravitational pull, then something else has to be there. Something we cannot see, something that doesn't emit light, doesn't reflect light, doesn't interact with light in any way we've ever managed to detect directly, and yet its presence is unmistakable, written quietly into the motion of every galaxy we've ever studied. Scientists call it dark matter, and here's the thing most people don't realize about that name. Dark doesn't mean black, the way a shadow is black, or the way the emptiness of deep space appears black to our eyes. Dark in this case means something closer to invisible, undetectable, matter that simply does not interact with light at all, neither absorbing it, nor reflecting it, nor emitting any of its own. It passes through ordinary matter, and ordinary matter passes through it, as though the two exist in parallel, brushing past each other without ever truly touching. The evidence for its existence first emerged decades ago, when astronomers studying the rotation of galaxies noticed something that shouldn't have been possible. Stars near the outer edges of spiral galaxies were moving far too fast. Based on the visible matter alone, they should have been flung outward into space entirely, unable to remain gravitationally bound to their galaxy at all. And yet there they were, orbiting steadily, held in place by a gravitational pull that the visible stars and gas simply couldn't account for. Something invisible had to be providing the missing gravity, something spread throughout and around each galaxy in a vast unseen halo. Here's where the scale of this mystery becomes almost impossible to fully absorb. Based on decades of careful measurement and calculation, scientists now estimate that dark matter makes up roughly 27% of the entire universe. Ordinary matter, everything you have ever seen or touched or measured, every star, every planet, every person who has ever lived, accounts for only about 5% of everything that exists. 5%. The overwhelming majority of the universe's mass is made of something we cannot see, cannot touch, and, after decades of dedicated searching, still cannot directly detect in any laboratory on Earth. And if that number feels unsettling, the remaining 68% of the universe is filled with something even stranger still. Scientists call it dark energy, and it represents perhaps the most profound mystery in all of modern cosmology. In the late 1990s, astronomers studying distant supernovae discovered something that shocked the entire scientific community. The universe isn't just expanding, the way it has been since the earliest moments, after its formation, nearly 14 billion years ago. That expansion is accelerating, speeding up. Galaxies are rushing away from each other faster with every passing year, pushed apart by some unknown force that seems to be embedded within the very fabric of empty space itself. Here's the thing that makes this discovery so quietly terrifying, in the gentlest possible sense of that word. Dark energy appears to be a property of the vacuum itself, of nothingness itself, actively pushing space apart faster and faster with no clear end in sight. It isn't a substance drifting through space the way dark matter seems to be. It is, as best scientists can determine, an inherent feature of empty space itself, growing stronger as the universe grows larger, because there is simply more empty space for it to act upon with every passing billion years. The very emptiness we've been describing all night, it turns out, is not passive. It is not simply the absence of something. It may be doing something, quietly, relentlessly, on a scale that dwarfs every other measurement we've discussed tonight. And this brings us to a genuinely strange realization, one that reshapes everything we thought we understood about emptiness itself. Space in the truest sense may never actually be completely empty at all. Even in the coldest, most isolated stretches between galaxies where ordinary matter thins out to almost nothing, dark matter and dark energy are still present, still active, still shaping the structure and expansion of everything around them. What we've been calling nothing throughout this entire journey may in fact be full, just full of something we have no way of directly seeing, touching, or fully understanding. Scientists have spent decades building increasingly sensitive detectors buried deep underground in old mines and laboratories, specifically designed to catch even the faintest possible interaction between dark matter and ordinary matter. So far, despite years of patient, careful searching, no detector has ever produced a confirmed direct detection. Dark matter remains, in the most literal sense, an inference, a conclusion drawn from its gravitational effects, rather than something anyone has ever actually observed directly. It is perhaps the most convincing evidence we have that something can be real and measurable and profoundly influential, while still remaining entirely hidden from view. And here is where the quiet, existential undercurrent of tonight's journey reaches its deepest point, because everything we've explored, the thin bubble of Earth's atmosphere, the vast gaps between planets, the trillions of miles between stars, the near total vacuum between galaxies, all of it exists within a universe that is, by mass, only about 5% the kind of matter we can actually perceive. The rest, the overwhelming majority of everything that exists, remains invisible to us, unknowable in any direct sense, using the tools we currently possess. We have spent this entire night exploring emptiness, only to discover that the emptiness itself may be the greatest mystery of all, filled with a presence we can measure but never see, and a force we can detect but never fully explain. Let's go back for a moment to the physical reality of all this emptiness. Not the mystery of what fills it, but the simple, physical experience of what it would actually feel like to stand within it, if standing were even the right word for something with no ground beneath it at all. Because throughout tonight's journey, we've touched on cold and silence and isolation many times, but we haven't yet sat fully with just how extreme those conditions become once you travel far enough from any star's warmth to feel their true weight. Here's the thing most people don't realize about the cold of deep space. It isn't like winter. It isn't like anything you have ever experienced on Earth, even in the harshest polar regions our planet has to offer. The coldest natural temperature ever recorded on Earth's surface was in Antarctica, dropping to nearly negative 140 degrees Fahrenheit. Brutally cold by any human standard. And yet, that number is warm, almost comfortable, compared to the average temperature of deep space, which hovers just a few degrees above absolute zero, somewhere around negative 454 degrees Fahrenheit. Absolute zero itself is not simply a very cold temperature. It represents the theoretical point at which all molecular motion stops completely, not slows down, stops. Every particle frozen in perfect stillness, with no vibration, no movement, no energy left to transfer to anything else at all. Scientists have never actually observed a natural location in the universe that reaches this exact point, but the coldest stretches of intergalactic space come remarkably close, drifting for billions of years at temperatures that would instantly, silently end any form of life as we understand it, without even the mercy of pain, because there would be no warmth left in the body to signal anything was wrong at all. And here's where the darkness deepens further still. In the vast stretches between galaxy clusters, far from the light of any star, scientists have identified regions so devoid of both matter and light that they've earned a particular kind of scientific fascination. These are sometimes called cosmic voids, enormous bubble-like regions of space, some stretching across hundreds of millions of light years, containing dramatically fewer galaxies than the average density found elsewhere in the universe. One of the largest ever identified, sometimes referred to as a supervoid, spans a region so immense that light travelling at its incredible speed would still take hundreds of millions of years just to cross from one edge to the other. Think about what it would mean to exist within one of these voids, if anything could exist there long enough to notice. No nearby stars to provide light or warmth. No nearby galaxies to break up the horizon in any direction. Just an endless uniform darkness, stretching for hundreds of millions of light years in every direction you could possibly look, broken only by the faint, ancient light of galaxies so distant that observing them reveals not their present state, but a version of themselves from an unimaginably early point in the universe's history. It is, in the most literal sense, one of the loneliest possible places the universe has to offer, and the darkness itself carries its own strange, unsettling quality beyond simply the absence of nearby light sources, because space isn't just visually dark, it's dark in almost every measurable way. There's no ambient glow, the way even a moonless night on Earth still carries a faint scattering of starlight and atmospheric glow. In the deepest voids, in the coldest stretches between galaxy clusters, the darkness is total, uninterrupted, and has remained essentially unchanged for longer than most galaxies we can observe have even existed in their current form. It is a stillness so complete that human language struggles to describe it without reaching for words that feel, honestly, almost too dramatic to be real. Here's the thing that tends to unsettle people most, once they really sit with all of this. Every single measurement we've explored tonight, every trillion-mile gap, every atom scattered impossibly thin across a sugar cube's worth of space, every degree above absolute zero, points toward the exact same conclusion. The universe, at its most fundamental default state, is not merely quiet. It is not merely dark. It is a place actively, overwhelmingly hostile to warmth, to light, to sound, to anything resembling the comfort you feel right now. Lying somewhere safe and warm, listening to this voice describing a coldness that stretches, unbroken, across nearly the entirety of everything that exists. And it's worth allowing that feeling to settle fully, just for a moment, because there's something important waiting on the other side of it. Because if the universe truly defaults to this kind of profound, total emptiness, cold beyond imagination, dark beyond anything Earth has ever produced, silent in a way our ears were never built to fully comprehend, then something remarkable has to be true about the small, warm pocket of existence we happen to occupy. Something that turns this entire unsettling picture, slowly and gently, into one of the most reassuring realizations this journey has to offer. And that's exactly where we're headed next. Here's the thing most people don't realize, and it's the kind of realization that changes how everything we've discussed tonight actually feels. That vast, cold, silent emptiness stretching across nearly the entire universe isn't simply the backdrop against which life happens to exist, in spite of it. It is, in a very real and specific sense, the exact condition that allowed life to exist at all. Without that overwhelming vacuum, without that near-total absence of matter stretching in every direction, none of what we know as reality could have ever formed in the first place. Consider gravity for a moment, and how it actually works across such vast distances. If space were dense, if matter were packed closely together, the way we might instinctively imagine a full universe should be, gravity would behave in wildly chaotic, unpredictable ways. Stars would form too quickly, too close together, colliding and disrupting each other constantly. Planets would never settle into stable, predictable orbits. The steady, patient rhythms that allow a planet like Earth to circle its star at a safe, consistent distance for billions of years depend entirely on there being enormous amounts of empty space between objects, space that allows gravity to act cleanly, predictably, without constant interference from overcrowded neighbours. And that emptiness plays an equally important role at the smallest scales too. Vacuum is what allows light to travel across billions of miles without scattering apart or losing its information along the way. If interstellar and intergalactic space were even slightly denser than they actually are, filled with more gas or dust than currently exists, starlight would struggle to reach us clearly across such vast distances. The very images we've captured of distant galaxies, the light that reveals the earliest moments of the universe's history, depends entirely on light being able to pass through, largely undisturbed, across an emptiness so complete that photons can travel for billions of years without significant interruption. Think, too, about the emptiness immediately surrounding our own planet, the same thin, fragile boundary we described way back at the very beginning of this journey. That vacuum isn't a hostile void separating us from something better. It's a kind of protective isolation in its own strange way. The near-total emptiness of space means that Earth orbits largely undisturbed by nearby debris, nearby collisions, or nearby gravitational chaos. The relative emptiness of our own solar system, that same vast gap between Mars and Jupiter we explored earlier, gave planets the room they needed to form stable, lasting orbits, rather than existing in a crowded, violent shooting gallery of constant impacts. Here's a detail worth sitting with quietly. Our own sun formed roughly 4.5 billion years ago, inside a relatively dense molecular cloud, one of those slightly thicker regions of the interstellar medium we described earlier. And it was precisely because that cloud was surrounded by so much emptiness, so much stable, quiet vacuum, that the material within it was able to collapse gradually, forming a star and a stable set of orbiting planets, rather than being disrupted by the gravitational chaos of countless nearby stars, all forming and interacting simultaneously. Emptiness gave our own solar system the room, quite literally, to exist in its current stable form. And this same principle echoes at every single scale we've explored tonight. The distance between galaxies, so vast that light takes millions of years just to cross it, is what allows galaxies to evolve on their own timelines, without constant gravitational interference from every other galaxy nearby. The distance between stars within our own galaxy is what allows planetary systems, like our own, to form and stabilize without being torn apart by a neighboring star's gravity. Emptiness at every level isn't the enemy of structure and life. It is the very thing that makes structure and life possible in the first place. And there's something else worth considering here too, something almost tender in what this emptiness has quietly allowed to happen. Because within all that vast, cold, silent vacuum, in an almost unthinkably rare pocket of stability and warmth, atoms did come together. They formed a star, our star, close enough to warm a small rocky planet, but not so close as to scorch it beyond habitability. And on that small planet, protected by a thin, fragile atmosphere, no thicker than the skin of an apple, something extraordinary happened. Matter arranged itself into a form capable of looking outward, into all that emptiness and beginning to understand it. That's you. That's every person who has ever lived. rare arrangements of atoms existing briefly within an almost unimaginably vast ocean of near total nothing, somehow capable of wondering about the very emptiness that made our existence possible in the first place. Out of a universe that is, overwhelmingly, cold and dark and silent, a tiny fraction of matter organized itself into something that can feel warmth, hear sound, and ask questions about why any of this exists at all. It is, without exaggeration, one of the strangest and most improbable outcomes that vast emptiness has ever produced. And so, as we prepare to bring this journey to its close, I want you to hold both of these truths gently, together, at the same time. The universe is, by every measurement we've explored tonight, staggeringly, overwhelmingly empty, cold beyond comprehension, silent beyond anything your ears were built to process, and yet, within that vast emptiness, in one small fragile corner of it, something rare and warm and alive managed to form anyway. Not despite the emptiness surrounding it, but, in a very real sense, because of it. The same vacuum that makes space feel so vast and lonely is the very thing that gave your own small, warm, breathing life the room it needed to exist at all. So let's bring this journey home now, gently, the way you might carry a candle back through a long, quiet hallway toward a warm and familiar room. We started tonight with the air around your own body, that thin, fragile bubble wrapped around a small blue planet. And from there, we travelled outward, mile by mile, billion by billion, trillion by trillion, through gaps so vast that the numbers themselves eventually stopped meaning very much at all. And now, having gone as far as this journey can reasonably take us, it's worth asking what all of that distance was really for. Because here's the thing most people don't realise until they've made a journey like this one. Understanding just how empty the universe truly is doesn't make our own small corner of it feel smaller. It makes it feel almost impossibly precious. Every planet we described tonight, drifting alone through hundreds of millions of miles of open dark. Every star, isolated by trillions of miles from its nearest neighbour. Every galaxy, separated from the next by millions of years of travel, even at the speed of light itself. And somewhere in the middle of all of that overwhelming, patient emptiness, one small warm blue world managed to hold on to enough atmosphere, enough water, enough gentle stability to allow something as improbable as you to exist. Think back for a moment to that image of Earth's atmosphere, thinner than the skin of an apple, wrapped around our entire world. That thin, fragile boundary is the only reason any of tonight's story could even be told. It's the reason sound exists at all, the reason your own breathing carries any weight, the reason warmth can gather and stay, rather than dissipating instantly into the cold vacuum waiting just 100 miles above your head. Everything you have ever loved, every voice you've ever heard, every quiet night like this one, has unfolded entirely within that same fragile, precious layer, suspended between a solid earth and an infinite darkness. And it's worth remembering, too, just how strange and rare it is that matter, arranged in exactly the right way, became capable of understanding any of this at all. Out of a universe that is, by every measurement we explored tonight, almost entirely emptiness, cold beyond imagining, silent beyond anything the human ear was built to register. A small fraction of atoms somehow organized themselves into eyes capable of looking upward and minds capable of wondering what they were looking at. We are not simply small, insignificant specks lost within all that vastness. We are the universe's rare, quiet way of noticing itself, of looking back at its own overwhelming scale and somehow making sense of it. There's a kind of comfort hidden inside that thought, if you let yourself sit with it for a while. Because everything that once felt unsettling tonight, the silence of interstellar space, the cold beyond absolute zero, the trillions of empty miles between even our nearest stellar neighbours, all of it becomes, from this angle, less like a threat and more like a vast, quiet canvas. A canvas so large, so patient, so overwhelmingly still that it made room for something as fragile and improbable as a warm, breathing, thinking life to emerge, if only in one tiny corner of it, for one brief, remarkable moment in cosmic time. And it makes you wonder, doesn't it, in that soft, drowsy way that tends to settle in near the end of a long story like this one. Somewhere out there, scattered among the trillions of stars we haven't even mentioned tonight, are there other small, fragile bubbles of atmosphere wrapped around other small, warm worlds? Are there other minds, somewhere, lying quietly in their own version of this exact moment, wondering the exact same thing about us? We may never know the answer. The distances involved, as you now understand better than almost anyone, may simply be too vast, too cold, too silent for that answer to ever reach us. But the not knowing, strangely, doesn't feel empty either. It feels a little bit like wonder. Thank you for staying with me through all of it tonight, through the thin, fading edges of our own atmosphere, through the vast, quiet gaps between the planets, through the cold, patient silence between the stars, and the even colder, even more patient silence between entire galaxies. If this journey helped you feel that same quiet sense of wonder, I hope it carries. Take a moment to like this video, or subscribe, so more curious minds like yours can find their way here too. It's a small gesture, but it means a great deal, and it helps keep stories like this one drifting gently outward, the way light does, long after the moment it was first spoken. And now, as you drift off tonight, I want you to picture that thin blue atmosphere one more time, wrapped so gently, so completely around everything you have ever known. Somewhere just above it, closer than most people ever realize, the vast, quiet universe continues on exactly as it always has, cold and dark and endlessly patient, holding within it, somewhere, a small and improbable warmth that managed, against every overwhelming odd, to notice it was there at all. The next time you find yourself outside on a clear night, take a moment to look up at the stars scattered across that endless dark. Remember that the space between you and each one of them is far vaster, far quieter, and far stranger than almost anyone ever stops to consider. And remember too that within all of that vastness, you are here, warm, breathing, wondering. That alone is worth carrying gently into sleep tonight. Sleep well and keep looking up at the stars. Good night.